We're a little bit behind in the syllabus. I'm not going to catch up today, but I want to not get further behind today, so I want to just zoom right along. So what I want you to do is remember the example that we've been doing forever. That's 2 full lectures, 2 or 3, which is this air track. I'm not going to show all the derivation again. We're going to just do demos and computers. Demos, computers, Blackboard stuff, not. Okay, so here's this thing. How does it behave? It's 2 masses, 3 springs. And if you start it in the right place, it does nothing. If you start it something like this, it does a complicated thing. Then you say, are there any simple things it can do? Well, if I start these exactly opposite, by symmetry of this problem, because these 2 masses are equal to each other, it has to stay symmetric. So if I move them just opposite and do it just right, it does this nice motion. Also, if I take the 2 of them and I move them just to the right like this, it does this nice motion. Okay, so before I go on, I want to talk about those 2 nice motions. This is a nice symmetrical system, so it's natural that you would think it would have maybe nice symmetrical motions like that. But the fact of the matter is that this result about these nice motions is much more general. How can I say it's more general? This is a linear system. It's linear homogeneous equations which describe this. Therefore, if I have 2 solutions, I can get a solution by the sum of those 2 solutions. If I had a solution like this, I could have sines or cosines. If I had a solution like this, so I could have sines or cosines. That means I have 4 different solutions of that type. And they're all sort of different from each other. If I try to launch these 2 things, I have an x position and a velocity for this, and an x and a velocity for this. I have 4 different things I have to match. 4 different positions, 2 different positions, 2 velocities. Yet I have 4 solutions, one like this and one like this, which I can superpose. Therefore, it turns out those solutions are linearly independent. Who is not or has not taken Math 294? So, not a prerequisite, but I'm going to cheat and take advantage of the fact and assume you've taken or are taking that class. These 4 solutions are linearly independent. The initial conditions are linearly independent in the space of x1, x2, v1, v2. Therefore, I can span the space of all possible initial conditions. Therefore, I can write any solution as a linear combination of the sines and cosines like this and the sines and cosines like this. Therefore, every solution is that. So that complicated solution, if I just move 1 to the side and it moves in this jittery way, it has to be a sum of the sines and cosines of those special solutions. Now that works for this problem. It turns out if I made the masses unequal, there's still special solutions. And if I make the springs unequal, there's still special solutions. And if I take any system with any number of degrees of freedom, so long as there's linear elasticity connecting the masses, there are always those special solutions. So what are those special solutions? They're called normal modes. And what are normal modes? They are solutions where if I make a cross plot of, say, x1 and x2, that the motion in the cross plot is a straight line, that the 2 masses move synchronously. So this one would correspond to the motion where the 2 are going like this, or I could get a motion like this where the 2 masses are moving opposite of each other. One goes plus, one goes minus. So as they're going back and forth, we're going oscillating on this. And if we want to generalize to, say, 3D, if we had 3 masses, we could plot x, y, and z. So here would be x1, x2, and x3. And there would be some crooked line in space. And it would go up and down this crooked line in space with all the masses moving synchronously. So all the masses move synchronously. Synchronously, however you spell that, which means that in the cross plot, or in the plot of positions only being plotted, not the velocities, not time, just the trajectory and position space, is a straight line back and forth. Some crooked straight line. If you have 100 masses, it would be a straight line in a 100-dimensional space. But it's always solutions that look like this. X of t, and this is now a list of numbers. is always going to be some constant 1, constant 2, constant 3, down here to constant n, if we have an n degree of freedom, times cosine of some omega natural t minus some phase shift. They're all moving in a cosine wave or a sine wave or a mixture of the two synchronously. It always happens. So as a general result, it follows from linear algebra and differential equations mixed together. You can read about it in the book. You can read about it in Wikipedia. You can learn more about it in later classes. I'm not going to get all into the math of it here, but I want to give you some demonstrations. So one is musical instruments. If you look at a string of a musical instrument, you can think of a string as a long line of springs and masses, hundreds and thousands of degrees of freedom, and it has some special motions. This is a normal mode motion, where all the different parts of the string are moving synchronously back and forth. If I look at this part, this part, this part, they're all moving synchronously together. That corresponds to this motion like this. On the other hand, the same system with all these degrees of freedom has other solutions. For example, this same string has this as a solution. So I'm not touching it, it's the same string, but I somehow started a different way, and it can do this other thing. And that's one where the different parts of the string are moving opposite each other. Now this string has lots of degrees of freedom. It has a different solution there. Now there are 3 different parts of the string. 2 on the outside are going up and down. 1 in the middle is going like this. I can't, if I do it with my head, it's going like this. And then there's more of them. And this string, because it has lots of degrees of freedom, thousands of them, there's more and more of them. Same string. All of those are normal mode vibrations. Now normal mode vibrations are all over the place. Here's another elastic system. It's a weird elastic system. Relative to an equilibrium position, I can write linear equations for this. And this has a normal mode solution. The lowest mode, the slowest one, is about like this. Now if I try to get a higher mode of this one, I can't, it's hard to find it, and I haven't found it successfully by shaking, but it has a whole sequence of modes. All of these complicated motions that you see are somehow a superposition of those simple modal solutions. Just like any sound that string makes, like now it sounds like this, but if I pluck it with my fingernail, it sounds a little different. Here, I'll do it like this. Now why does that same string sound like this and sound like this? Is because it's got different amounts of the different modes in it, and they call it different harmonics in the case of a string. So what your ear picks out is that's actually more of the higher harmonics, and it sounds more tinny. This is more of the lower harmonics. Okay? Now, this is an example that I used to do in this room before they remodeled it. They've ruined this classroom. They spent $1 million fixing it up, so this demo no longer works, but I'll try it anyway. So this is a bottle of air. Air has mass. Air also is a little springy. It's compressible, so it's mass and spring, therefore vibrations. Therefore, it has all kinds of motions. It's got normal mode vibrations. If you can excite those normal modes, it makes music, and this also makes music. Now you have to be completely quiet, and you have to ignore that stupid air conditioner. Who can hear it? Front row can hear. Can you hear it on the video? Yeah, we're going to go for this. Do you have your earphones on so you can? Okay. You got it now? Cool. Oh, wait a second. Video, so I'll just give the experience to some random person in the audience. Raise your hand if you want to be that random person. Okay, so now watch his face and you'll understand what pleasure you could get from this. Okay, so now let's go back to this. Any questions about normal modes? I'm going to go on with normal modes, but in this example, but that was meant to be general inspiration. Any questions about the general inspiration side of things? Okay. Take this system. What would happen if I took away this spring? Now, in this case, these springs stink. So let's imagine that they had a rest length out here, so these could oscillate like this. And let's say I made this mass a little smaller, and I launched these from rest at equal velocities like this. What's the motion I would get? Okay, so let me set that up on the computer. Let's say you want to watch it too. We could do center display on. Cool. Okay, so here's the same code that we've been looking at for a while. And now I'm going to put in, let's run this for about 2 pi. Let's put initial conditions of some velocities like this. Let's put in no initial positions. Let's make the second mass be 0.44, just some sort of random thing. Let's make the second spring constant 0 and run this. What do we get? Well, we get 2 independent oscillators. One of them is going faster than the other. Why are they independent? Because that coupling spring is 0 and the damping was 0 too. And one of them is going faster because it's the same spring, but a smaller constant. One's going slower. Okay, so now I've got a visualization exercise for you, which is if I make a cross plot where I plot x2 on the y-axis and x1 on the x-axis, what is the shape of that cross plot? Okay, look at the screen. What is the shape of that cross plot? Let's see. Did anybody see, I was quoted in the international news yesterday. Yeah, the Cornell engineering undergraduate leaflet had about my sister, feeling sorry for poor me. Okay, so here's what you guys say. Now, there is a question about these kind of questions, whether it's social dynamics or mechanical dynamics that we're studying when we look at these things. Okay, 5 more seconds. 1, 2, 3, 4. 5. Okay, we lock it up. Now we go back to the Matlab. Hide this plot for a minute. So now let's look at the cross plot. There you go. It's from me to you. Okay, so how does that work? Look, you look at one of these, the x-axis, it does about a whole oscillation. The x-axis goes over to the right, back to the left, and over to the right, and stops. And there you have the x-axis over to the right, back to the left, over to the right, and just about stopping. And then the y-axis is the one going faster. It goes up, down, and up. There's a whole oscillation, and then up again and down. And so there it is. It goes up and down and up. There's one oscillation of the y-axis, up, down, and up. And then it does another like half oscillation, and that completes the picture. Yes? What if we let this go for a long time? What does this do? Now, you can do this at home, but it's fun. This just a system with two oscillators is fun. Okay, so these kinds of pictures have a name. They're called Lissajous figures. They're what happens if you take two sine waves that have different frequencies and you make a cross plot. You get Lissajous figures. Lots of science museums have little sand pendula that draw these pictures. And if you look back over here, it's not so interesting. Okay, so one thing we see over here is that even though we've got this teeny time step, I'll just make this step teeny 100th, but not quite so teeny. I've got the energy increasing in time, and this is not physical, right? This is energy increasing, and that's a numerical artifact. So we'd like some more accurate numerical integration. So working our way up in our plan, to get you to write better programs, computer programs, we want to do more accurate integration. So if we look at just how does Euler's method work, so let me go over here and look at Euler's method. I want to improve Euler's method. So let's look at an example problem, which is say that z dot is equal z. Just one variable, not a list of variables, and so on. This is a plot that this is one that we can graph easily. We can put t here, and we can put z here, and we can represent the differential equation by a bunch of slope lines. If z is equal to 0, the slope line is 0. If z is equal to 1, there's a slope line of 1 here. If z is equal to 2, there's a slope line of 2 here. If z is equal to 5, there's a slope line, a much steeper slope. And we can fill the whole plane with constant slope lines. And what we know is the solution of the differential equation is going to be something which is everywhere tangent to these lines. So the exact solution of this differential equation is something like this. So here's the exact solution. If we're given, for example, z of time equals 0 is equal to 1, the exact solution is z is equal to e to the t. And here's this e to the z solution. If we track it, it looks like that. The Euler method solution starts here and takes a step, goes here, and goes like this. And this is the Euler method solution of this equation. Is this much clearer? Any questions about what I drew here in terms of understanding Euler's method, exact solution, and so on? So this is not so good here. Now we've got a trick. What we're going to do just now, and I'm going to do it on the computer, is I'm going to go here. I'm going to measure this slope. I'm going to use this slope back here, and I'm going to take a step like that. And this is an improved method, and it has various names. It's called the midpoint method or the two-point Runge-Kutta method. And you can see that by the time I take a step, actually I should have drawn this, if I use the same h value, it would go over to here. It's much closer to the exact solution. Is that clear what the method is? I'm going to take a half step. I'm going to measure z dot here. I'm going to use that z dot to take a whole step, and I'll end up much closer to the exact solution. So I'm going to use that idea now for this coupled oscillator equations, and I could use it for any equations I want. So now I'm not going to do Euler's method. I'm going to do improved midpoint method. And midpoint method goes like this. I've got z dot, and I'm now going to call this z dot temporary. And that's going to be right-hand side of t ZP. Now I'm going to go Z nu temporary. And I'm only going to take a half step here. So I'll go H over 2. Now that I've got this new Z nu temp, I'm going to go back and I'm going to calculate a new Z dot. And I'm going to calculate it by taking this right-hand side. And I'm going to evaluate it now at, instead of at Z, I'm going to evaluate it at Z nu temp. Okay, so far, I started out by measuring the derivative here, just like I did before. I took half of an Euler method step to give a new value of Z. Then I'm going to take half of a time step to go with that. So at this new place, I'm going to evaluate time and this new position. Then I'm going to get a new value of Z dot, and then I'm going to go back, and I'm going to say my new value of Z, my Z nu, is going to be equal to my original value of Z, which was Z plus, well, I'm just going to copy my the original line I had here, but with H instead of H over 2. So I took half a step, used that provisionally, measured the Z dot there, went back to the beginning and took a whole step like that, and it should come out much more accurate unless I made a mistake. So now I run the code again. I'm doing twice as much calculation as I was doing, so it should come out more accurate anyway. I run this thing and probably have some error of some kind. Euler's method, the heart of, well, one mistake, the heart part was good for today, but the Euler's method part isn't good. And it said undefined function or variable Z dot. So let me go back here. That was line number 32. That was Z dot temp. And this is not the heart of Euler's method anymore, even though the heart part is good for today. This is now a half step. Okay, now let's try this again. And look, energy is conserved really well. Yes?
How would you compare with just decreasing the step size?
Okay, so here I did twice as much work. So in terms of the amount of calculation, this would have been like taking a step size of, where do I have my times in here? I have up here, I have a step size of 0.01. So to be fair, I should compare this with twice the step size in terms of equal amounts of calculation. So now I put in twice the step size, and now I can compare this to what I had before and see how it works out. And look, it's still really good. In fact, I can put in, let me just be radical here and put in 10 times the step size, and it's still pretty good. So it's not like, oh, I did twice the work, it's twice as good. It's like making the step size half as good. It's way, way, way better. Okay, if I can tell a story from my own life, I didn't take a course with a professor like me that explained these things. And when I was a graduate student, I had to solve some differential equation on the computer. And back then we had disks like this and only 32 all that stuff. And it was a big, slow computer. And just to do a simple calculation, not much harder than this, I was waiting all night to get accurate solutions. And my girlfriend at the time, that's when I did get real Valentines, she was a graduate student in computer science at Stanford. And she said, you know, there are people who know how to do these things better. And I said, I don't need that. I understand differential equations. It's just a crystal ball. You just take one step in the future, and that tells you what's going on, and take another. She goes, no, it's more sophisticated. I said, no. But anyway, eventually, she gave me this stack of books, and I took one of the books, and in one of the books, there was a chapter, and I read the chapter, and it went on and on and on about all the ways you could solve differential equations. And it started with Euler's method. It was completely confusing. And the last sentence of the chapter was, it should be remembered that all of these methods converge extremely quickly, except for Euler's method, which is the one I taught you until just now. So I went back to the chapter, started with Euler's method. It said the first simple correction to Euler's method is the midpoint method. I said, very good, use that. And you look how much better it is. So now we did 1/20th as much computation, and we get a much more accurate answer. Okay, I can even make it a 40th. It's still a very good answer. Okay, now we're starting to see a little gain in energy. So this midpoint method is a huge improvement. Now, when we go to the official stuff that real people use, like what Matlab wants you to use, ODE 4.5, that's even more accurate, much more accurate. But this is such a huge improvement that it's good enough. It was good enough for my PhD thesis and more. Okay, so any questions about this method? Does that address your question about how it compares? Any other questions about this method? Okay, so now there are other little things we can do here. Let's go back to the cases where we had k equals 1, where it looks like the setup there, and where the masses are about equal to each other. I don't have the right values for the masses, and I don't have the right values for the offsets, but in terms of the motion, this is about right. Let's put in initial conditions. It's starting nowhere, but let's run this thing with excitation at the end, with just a little bit of excitation at the end, which is at one of those natural frequencies. And what you see is just like with the harmonic oscillator. First of all, in this cross plot, you can't see it, but it's just bigger and bigger amplitudes almost on this line, not quite, because it's not the raw system, it's the forced system. And what you see is just like with the harmonic oscillator, this increase in oscillations. And then last class, I tried to show you that if I put square root of 3 here, it didn't work at the end of last class because I had a different mistake. That's this other mode, and here's what it does. Also, now the two are moving oppositely, but we still get this resonant phenomenon. And if you think, oh, this is just math mumbo jumbo, we take this thing, this machine. I'm going to turn it on. I'm going to put this little spring back in. We'll just start it right here at 0. Let me just repeat that. I'm going to put the spring back in, put them in the rest position, and start it at 0 and turn on the fan. Okay, then I'm going to turn on the fan and turn on this motor here, which has been set to be at this desirable frequency. And what you see, so you force it at the right frequency. It's like me at the Golden Gate Bridge. You do the right thing at the right frequency, and you build up this this motion. Now, if I run it for a long enough time, the damping is so low, it will do that funny thing of decaying again, because these oscillations will be out of phase with these oscillations, but it does about the right thing. Okay, any questions about this demo or anything so far? Okay, now moving along here. Remember in this code, we had to write the differential equations. And here are the differential equations. I cleaned it up a little bit from last time to make it easier to read. Let me just review the differential equations. We come in with a list of values of z, which are representing x1, x2, v1, and v2. I say, oh, the first two numbers are x, the second two numbers are v. I've got some forcing function I'm going to calculate. Let's calculate the lengths of the springs. Here's the lengths of spring 1, here's the length of spring 2, here's the rate of change of length of spring, of the distance between the two blocks, here's the length of spring 3. Let's calculate the spring tensions. It's the constant times the length minus the rest length, the second spring length minus rest length, and so on. So this is all readable code. Then I plug in my differential equations, x dot equals v. First two differential equations are very simple. And the second two differential equations are that F equals ma, divide by mass. It says the rate of change of velocity is the total force divided by the mass. And the total force is just some tensions pulling to the right and left, and the same with the other one. And then I assemble these two accelerations into a list of two numbers I call v dot. Then I assemble four numbers, x dot and v dot, and that's the rate of change of these four numbers. So there's this rate of change thing. This is the thing that gets fed back into Euler's method or improved Euler's method or Midpoint method and so on. So these are the differential equations. Now, I've written them out in this expanded form. In effect, though, this is what's called a Matlab function. What's a function? It's something that takes inputs and gives outputs. In math, it's put real numbers in, real numbers out, or a list of real numbers in, list of real numbers out. Could I write that as just a simple function, like in math land, sines and cosines and so on? So that is, could I take all these things and substitute, and write a single function? And I could. So I could write out a single function, and I did that here. It looks like this. Why do I show this to you? Because I think this is bad programming. This is the kind of thing that when I was a sophomore in college, I thought, oh, it's cool. I can put it all in one line. Now I think that is really not cool. It's a bunch of unreadable stuff. There's a mistake in there. I'll never find it. Okay. But conceptually, you can think, oh, I take all this stuff, take all this basic, simple ideas, do all these substitutions, and I get down to something like this. Okay, now how did I do those substitutions? I'm really bad at math. I went into Matlab. I copied down almost that same set of code that I have there, but I ran that code as a symbolic code, so I made this all symbolic, and it did all this algebra, and it calculated this thing, and the output of this code, running it, came over to the display over here, and it was this. This is the answer, which I cut and pasted into the other program so you could read it. Okay, any questions about that? This is a symbolic toolbox in Matlab, which is what the symbolic toolbox in Matlab, in case you don't know it, is very much like Mathematica or Wolfram Alpha or Maple or some of you have, who has an algebraic calculator, a symbolic calculator? Raise your hand if you have one, if you own one. I know a bunch of you own ones. Do you have anybody have a calculator that you type sine, S-I-N, and to ask for the derivative it says C-O-S, cosine? There's more than graphing calculators. They're called, there's a name, symbolic calculators, I think they call them. Okay, I know a bunch of you have them, but I was trying to prove a point, which was that nobody knows how to use them, which is apparently true. But in Matlab, it's easier to use than on those calculators. Okay, now I want to go on. I want to be done with springs and masses and dashpots and normal modes and resonance and the equations of motion and Matlab and Euler's method and all that. We'll come back to some of it, but I want to be done with that for today's lecture. But somebody has to ask me one question. Yes, please. A cross plot is if you take two graphs, x1 versus t and x2 versus t, and you take for each value of time, you take the x1 from one plot and the x2 from the other plot, and you plot one on one axis and one on the crossing axis, and put a dot there. That's called a cross plot. So you have x1 of time, x2 of time. Now you plot x1 versus x2 for the same set of dots. So that gives you, in the case of this oscillator equation, we had x1 versus time and x2 versus time, and then that Valentine was x1 versus x2. It was a trajectory in the configuration space, or in the position space, rather than the trajectories of positions versus time. But in general, cross plot is kind of an old word. Maybe it's like a 19th century word. It means takes two graphs, which are parameterized by one thing, and then take those vertical axis ones and plot one vertical axis against the other vertical axis. Does that answer your question? Another question? Okay, so now we go on to a new topic. Is collisions. So my basic picture is going to have M1 and M2, and this one initially is going to have V1, and this is initially going to have V2, and they're going to bang into each other, and I want to know what their velocities are afterwards. So first of all, there's a notational issue. Sometimes people talk about this with different notations. So we have the before and the after. And I just want to show you various notations. I just noticed this notational confusion. We could have V1 before and V2 before, and then we have V1 after and V2 after. But another thing we could have is VA before and VB before, and we could have VA after and VB after. And another thing we could have is V1 before and V2 before and V1 after and V2 after. So what I want to show you here is that there's confusing notation. The confusion is sometimes you use A and B for blocks A and B, and sometimes you use A and B for after and before. This is not a technical point. This is just a confusing point in the notation in terms of how different people write things. And I write things sometimes one way, sometimes another. OK, so now we've got these blocks that are going to collide into each other. So we take away these springs. And these things are going to bang into each other. Who's seen this demo? Raise your hand. Half of you. OK, so now we're going to turn on the air track again and have these bang into each other. So this one's initially still, say, slow down. And I come in and bang this into it. So this is what's called an elastic collision. They come in at some speed and they separate at the same speed. So what happens in the collision you characterize with a material property or an object property, which is what's called the coefficient of restitution. In this case, the coefficient of restitution is very close to 1, and we get this motion like so. A different coefficient of restitution we could get by destroying this equipment by Dave's going to kill me. We want to get a plastic collision. So some disgusting person left a piece of gum down there. So we put a piece of gum here, and then we get a pretty plastic collision. The word plastic comes from the word, I think it's Latin, it means clay, and then they more or less stick to each other. So that's a really dead collision, like that, versus the live collision, like that. So here it plugs in pretty plastic, not totally. So the coefficient of restitution here is not quite 0. If I want to make it 0, I have to make the gum wet. Okay, it gets more and more disgusting, right? Okay, any questions about this demo? Now, if you were really my Valentine, you wouldn't be disgusted by my spit and all that stuff. You would just tolerate it, you say. I love him anyway. Okay, now I can throw it away. Let's say we want to calculate what goes on in this kind of thing. To make this class a little faster, I did some coding ahead of time because we only have so much time. So we've got this collision, and now I'm going to use this notation where the masses are called 1 and 2, and B means before, and A means after. So let's say I have the first mass has a velocity of 2 coming in, and the second one has -2. From your point of view, here's 2, here's -2. They're going to come in and bang. Let's say the masses are equal. For simplicity, let's say it's 1. Let's say the coefficient of restitution, let's make a simple one here, is 0. So these are my inputs to the problem, and now I want to calculate the output. How do I calculate the output? I have 2 basic equations to work with, which are these 2 equations. What are they? The total momentum of the system before the collision is the sums of the masses times the velocities. And the total momentum of the system after the collision is the sums of the masses and velocities. And there's no external forces on the system, so the momentum of the system before and after matches. I could also get this equation by taking F equals ma for each mass, using action and reaction, and adding those two equations, and find out that the force of interaction drops out, and then I get that the net change in velocity of the sums of the masses times the velocities is 0. So that's one equation. The other one I have here is the restitution equation. And what it says is, look at the relative velocity of the two masses before the collision. That's v1 minus v2 before. Then multiply that by e, and that gives me the relative velocities afterwards reversed, because now they're separating. So this is the basic restitution equation. This is taken as a material property. Remember the second pillar, or the first pillar of mechanics of material properties. We assume that the objects have this property, and this has to do with, for example, gum is E is about 0, and those coil shim stock springs between them, E is about 1. So these are two equations and two unknowns. But I've organized these equations so all the stuff I know is on the right-hand side, because I know the initial velocities, initial masses, and I know the coefficient of restitution. And the stuff I don't know, the velocities after, is on the left-hand side. So it's two equations and two unknowns. They are linear in the unknowns, which means I can write them in matrix form like this, where this is a 2 by 2 matrix, A is a 2 by 2 matrix, and this is a column vector of right-hand side stuff. So if you pick out the coefficients of V1A and V2A, it's M1 and M2. So those are M1 and M2 in this matrix, and minus 1 and plus 1, that's minus 1 and plus 1 in this matrix. I look at the right-hand side, I've got this number followed by this number. So here's the first number followed by the second number. And I've got to then solve this matrix equation. A is given, all the coefficients. The right-hand side is given, which came from initial velocities and masses and coefficients of restitution. And unknown are these two velocities. Okay, is this setup clear? So the two basic equations, momentum balance and the restitution equation, are two equations and two unknowns, the final velocities. They're linear equations. I can organize them in matrix form, and therefore I can use matrix commands to solve it. So whether you've learned this or not in Math 294, here's how you solve it. Now, did you learn this in Math 294 or not? This is a question about, is Professor Hoy a good professor or a bad professor? Did Professor Hoy teach you this in Math 294 or not? He did? He's a good professor. Okay. So this is this little symbol here is the Matlab's great backslash command. All of your course, Math 294, is basically about how this command works. That little one symbol. But for now, if you have a set of n equations and n unknowns, you want to solve them, and you don't want to take Math 294, you write them in matrix command, you use the backslash command, it gives you the answer. Now what's the answer? It's a list of two numbers. We can take the first number and call it V1 after, the second number and call it V2 after, and then we can calculate a bunch of stuff. Like we can calculate the kinetic energy before, the kinetic energy after, the velocity of the center of mass before, the velocity of the center of mass after, and then we can print out all this stuff. So here's some fancy MATLAB commands for printing things out. You know, if you just type a variable in MATLAB, it prints it out, but it takes a lot of space. Now we don't want to take so much space. So let's look at the output of this calculation. Okay, let me not distract you with a bunch of stuff which came from before. So I run this thing called collision, and this was my output. So I had to print out the coefficient of restitution. I had to print out the velocity of 1 before, of 2 before, then 1 after, and 2 after. So here was a plastic collision, so they went in the middle, stuck, and didn't move. So the velocities afterwards were 0. And the kinetic energy before was 4. The kinetic energy was after. They're both 0. They went bang, no kinetic after. And I can do a check. What's the velocity of center of mass before and after? And no matter what the collision is, I better get that the velocity of center of mass before and after is the same, because the linear momentum of the system is conserved. I can do this again with a coefficient of restitution of 1 and run this thing. What happens then? Did I succeed in running it? Coefficient of restitution is 1. And now what happens is, look, the velocities reverse. One was going to the right, the other to the left, and then they switched. Bang, popped off. What happened to the kinetic energy? It was conserved. What happened to the linear momentum of the system is 0 all the time. Okay, now I give a little puzzle problem. I won't put it on the quiz, but what if I put a coefficient of restitution of -1? You got 15 seconds to think about it. Talk to your neighbors. Okay, what happens with -1? Anybody want to volunteer an answer? Raise your hand. Raise your hand if you have an answer. I know that you know the answer because I heard you mutter it before, so I'll go to you. You have it right? Or you had it right before you thought about it? Yes?
It'll be like they didn't fly past.
And you have it right too. So what happens is they just don't interact at all. They pass through each other. So let me run this code with this change in it. See what the output is. Here I've got coefficient of restitution is -1. The velocities before equal the velocities after. And I can put in any different velocities here. So the computer code for this is simple. If you want to do these two equations and two unknowns by hand, the convenient thing to do is to change to a center of mass coordinate system, and all that's explained in the book. I'm not going to cover it in lecture at all. But center of mass coordinate system simplifies it if you don't want to use the computer. Class is over. See you next week.